Algebra 2, 5.2, evaluate and graph polynomial functions. So to give us the big picture again of what's going on, every chapter in this textbook is based around a certain kind of function. And we look at solving, we look at graphing, we look at characteristics and how to identify, word problems associated with. So we have spent time looking at linear equations. We solved, we graphed, we had systems. We even looked at inequalities for linear equations. And then our last chapter, we shifted to quadratics. So we're looking at stuff that was degree 2, that was x squared. And we worked with those quadratics and we graphed and solved. So now we're extending what we know about solving equations to polynomial functions. So in 5.1, we spent a little bit of time working with exponents and getting a review on that. And when we say polynomial functions, we're really looking at something like this. You know, I have a number times x to the fourth, and then plus a number times x cubed, and on down. So we needed that little refresher on exponents because we're working with these higher powered functions right now. But polynomials is a really big umbrella. So if we're looking at polynomials of degree 0, that's my first one here. The type is constant, and that's because if I have degree 0, I have x raised to the 0 power, which is just a 1. And so if I have a 1, I have no variable. So no variable means it's not varying, it's constant, it doesn't change. So my example over here is f of x equals negative 14 or y equals negative 14. And again, I don't have an x in there, so x is to the 0 power. If I have degree 1, it's linear. So think y equals mx plus b. So here we have an example of 5x minus 7. If it is degree 2, it's quadratic. And we're pretty good at quadratics. Degree 3 is cubic. So you can see I have an x cubed in here. And quartic is degree 4. So when we talk about degree, just to kind of review our Algebra 1 language, degree is going to be that term that has the highest power of any of them. And so you're always trying to find that one. That's how you identify. It's not always the first one because they might not be in order. The other thing that I want to add is if I'm looking at like this 2x squared plus x minus 9, that 2, that first coefficient is called my leading coefficient. So in order to be polynomials, exponents must be whole numbers. So no fractions or negatives. No variables as exponents. That means you can't have like x raised to the y power. It has to be a 2 or a 3 or a 5, some kind of whole number. And the coefficients must be real numbers, and that means not imaginary. So that is how we help identify a polynomial. Some of the things we look for. So basically, it's x's and numbers being multiplied, and then you've got strings of plus and minus in between all those terms. So for example 1, we're going to be looking at whether or not the function is a polynomial. And if it is, we want to write it in standard form. That means descending powers and state degree, type, and leading coefficient. So the first one, it says f of x is 6x to the 1/2 power minus 5x. Well, 1/2 is a fractional exponent, so we'll say no, it's fractions. So we cannot have a square root, we cannot have a fraction, we cannot have a negative there, we can't have a variable. My second one looks good. I know that square root looks weird, but it's only on a 10. It's not on an x, so it's okay. So I want to write it in standard form. That means descending order. So x to the 5th is okay to have first, but then I should have 4th, and then squared, and then square root of 10 is my constant. And my degree is 5. Degree 5. Type quintic, but degree 5 is fine. Leading coefficient would be the negative 8. And then on problem C, let's see, negative 3x to the 4th. Oh, second one, I have a negative exponent, so I'm going to write no, it is negative. So now that we know what a polynomial is, we're really interested in what polynomial graphs look like, what kind of characteristics they might have. And so one of these things we talk about is end behavior. So when we talk about end behavior, we are talking about these little tails on the end of the graph and where they are going. And so we have one of them on the right, and the one that's on the right is as x goes to positive infinity. So that's this over here. And we're wondering about what does our y do? Well, our y is going up on that side of the graph. And so we say that our y, remember f of x is just y, our y goes to positive infinity. And then if I am looking at the left-hand side over here, that's as x goes to negative infinity, my y is also going down. So my y is negative infinity. So we're looking on the right and the left. So this first graph that I was talking about, I just kind of jumped right in and told you what we were looking at on the graph. But this is any polynomial function that has an odd degree. So by odd, we mean first, like linear, or cubic, or fifth, or seventh, or on and on and on. And the leading coefficient is positive. So when we are looking at odd degrees, and again, degrees that are linear, cubic, fifth, seventh, that's 1, 3, 5, 7, any odd power, I'm really thinking about a line. A linear equation was our first odd graph that we looked at, our first odd degree graph. And when we had a linear equation with a positive slope, the line went up from left to right. And this one you can kind of see where it's like a line that goes up from left to right. So that gives us kind of the shape of the graph. It's going up from left to right, but then this stuff about end behavior is what we're really interested in right now. And we're just going to do the best we can with that right now. I know it's new. The notation is really strange. Looking at that positive infinity and negative infinity, we've never really thought about that before, having the f of x instead of the y. So we just want to do the best we can with that right now. The next one is when we have an odd degree, but our leading coefficient is negative. So think about a line with a negative slope. So a line with a negative slope goes down, and that's what this graph is doing. And on the left here, so on the left is negative infinity. This little tail end of my graph is going up, so y is going to plus infinity. If I am looking on the right-hand side, so that's as x goes to positive infinity over here, here's my graph going down. So my y is going to negative infinity as x is going to positive infinity. So those are those odd graphs. So odd graphs are always going in those opposite directions. When we look at even graphs, we want to think about parabolas because a parabola is degree 2, and that was the first even graph I knew anything about. So when we say even, we mean 2 or 4 or 6, any of those degrees, 8, on and on and on, but they really all resemble parabolas. So if I had a y equals a positive x squared, I know my ends of my graph went up on both sides, just like it does here. When I have a positive leading coefficient, it's going up on both sides. And you'll so as we go to the right, as x goes to positive infinity, my y is going up to positive infinity. Same thing over here, y is going up to positive infinity on the left and the right. And then last is negative leading coefficient, but an even graph, that's like a y equals negative x squared. Both of the ends of my graph are going down, and so that's why we say here that y is going to negative infinity for both of them. So this is called end behavior. So again, we're just getting an idea about what kinds of things go on with polynomials, what those graphs look like. So to kind of further our idea, we've looked at how the ends should be on our graph. We want to get an idea about its basic shape. So when we have first degree, we're talking linear. And so we could have a line like this. It's going up, it has positive slope. We could have a line that's going down that has negative slope. I can have a line with a really, really shallow slope, but not 0. That would be a constant. That would be degree 0. I could have a line with a fairly steep slope, but not a vertical line. Vertical line wouldn't even be a function. A vertical line is not considered a function. So second degree is going to be my quadratics. So I can have just a normal looking parabola. I can have a skinny parabola that's been stretched vertically. I can have a parabola that's upside down. I can have a parabola that's upside down and stretched way out, like a 1/4 x squared or something. So third degree is cubic. And let's think about how third degree looks. So the interesting thing is I start out with a line, and then when it's quadratic, I basically am like adding a hump to that. So now I have a curve. So when it's cubic, I'm going to add another hump, and the other hump is going to take an end of my graph. So instead of having a graph that goes up and back up for cubic, it's going to go back down because they're going to go opposite directions. So I end up with 2 humps on it. And you can see this one would be like a negative x cubed because it's going down. I could also have one that's going up. I could have one that's kind of stretched out where there's barely really any humps there in the middle. I could have one where they're really, really deep and pronounced. So all of those would be considered cubic. So when I look at a fourth degree, if I look at a quartic, basically I am just going to add another hump to that graph, to the last one I had. And so that means my quartics could look like a W. This one would be positive. It could look like an M, so a negative, because they're going down. I could have one where they're kind of just this weird, almost like a straight line in between, but it's not. Like it's a weird, funky kind of curve. Or you could have one where those humps are different sizes. We could make another one like this. So all of those would be considered quartic. And it's also good to note that sometimes quartic graphs can even look like parabolas. They're just going to be stretched at a different rate because they're fourth power instead of squared, but they could just look like a quadratic even. So anytime you have a fourth degree graph, it could simplify down, or a sixth or an eighth, any even degree graph could simplify down to look like a quadratic. So fifth degree, we're just going to add yet another hump. So I could add another hump to my quartic degrees. So I have 1, 2, 3 humps, but then instead of just going up, I'm going to go back down. I'm adding like one more hump onto that graph. So that's fifth degree. We'll make one that goes up. And then I think that's really pretty much enough. These could also look like cubic though. So I'm going to make one like that again too. So just to give you an idea about graph shape. So the reason we're doing all this, we want to be able to think critically and just look at pictures and have some kind of an idea about the function we're looking at. And then we also want to use this to further our ability to graph. So if I look at example 2 here, you're going to have a lot of problems like this where they want you to comment on end behavior or say something about the equation just by looking at it. So this is asking me, what is the degree? So like 1, 2, 3, 4, 5, whatever. What do you think x is doing? Is it squared? Is it cubed? And what is true about the leading coefficient? So when we say that, we are really asking positive or negative. So what I notice is this looks like an M. So I'm going to guess degree 4. And it really could be sixth. You know, that could reduce down to look like a degree 4 graph. It could be 8. That could reduce down to look like a degree 4 graph. And then positive or negative. Well, both of these ends on my graph are going down. So I am going to say negative. So that's kind of what we're looking for there. So now we're going to do something completely different that is not just drawing a bunch of squiggles. I was joking a lot about that when we were doing this lesson in class today, that we're just drawing a bunch of squiggles, but there's right squiggles and there's wrong squiggles. You got to pay attention and get them right. And now we're going to look at something that's actually math. So we are going to do synthetic substitution. So synthetic really means fake, and that is exactly what we are doing. We have a fake way to substitute in math. So I want to find when x equals 3. So I'm going to put a 3 over here. And this is the equation I'm substituting it into. F of x equals 2x to the fourth. I'm just rewriting it, minus 5x cubed. And when I rewrite it, there's no x squared term. So I am going to write a plus 0x squared and a minus 4x and an 8. So now my powers are in descending order, and I have like that 0 as a placeholder. My powers go 4, 3, 2, 1 constant. So my constant is like the 0 term for x. X to the 0 power would fit right in there. And I have that 0x squared as a placeholder. So now I'm going to take my coefficients here, 2, negative 5, 0, negative 4, 8. Those are the numbers I'm using. And I'm going to write them to the right of the 3 in a row. So let's just review where these numbers come from. The 2, negative 5, 0, negative 4, 8 are the coefficients from my polynomial. And it says when x equals 3, that's the value I want to plug in for 3. So since I'm substituting 3, but I'm using my fake substitution, I put the 3 over here. So now I'm going to leave about a row's worth of space, and I'm going to draw a line. And then I am going to bring down my leading coefficient. I'm going to bring down the 2 below that line. And then we're going to do this pattern where we multiply it back, or multiply. And we're going to write it underneath. And we're going to add. So 2 times 3 is 6. And then I'm going to add, I get 1. And then I'm going to do 1 times 3 is 3. And then I'm going to add, and I get 3. 3 times 3 is 9. I add and get 5. 5 times 3 is 15. I add and get 23. So I started by just bringing down the 2. So I didn't multiply the 2, I just brought down the 2. And then after that, I multiplied and I wrote it underneath the next number and I added, and I followed that pattern, that multiplying and adding pattern all the way across. So the way this works out is the number I get at the end is the value I would get when substituting x equals 3 into that function. So basically what that means is that f of 3 equals 23. So I could also use direct substitution. So direct substitution is not fake. That's where I actually put the number in for all of the x's. And I know you're probably thinking, like, why didn't we just do that? That would mean 2 times 3 to the 4th minus 5 times 3 cubed. Let's see, minus 4 times 3 plus 8. I know that this is the way you've always done math. It wasn't a big deal, right? So let's just try it really quick. So 2 times 3 to the 4th. Well, fortunately, I know what 3 to the 4th is. I would bet a lot of people don't. That's 81. 5 cubed is 27. And then I have a minus 12 and a plus 8. Let's see, what do we have now? 2 times 81. I can still do that into my head. 162. 5 times 27. Let's see. 5 times 20 would be 100. 5 times 7 is 37. So 130. Wait a minute. 135. 5 times 7 is 35. So already I'm kind of questioning myself and maybe not doing a good job. The numbers that I'm getting are really big. Look at this problem up above where I did synthetic, where all I did was multiply and add, and the biggest number I got out of the whole thing was 23. To do 162 minus 135 minus 12 plus 8, I'm going to either have to really, really think, or I'm going to have to grab a calculator, or I'm going to have to even go over here and line up those numbers. So the idea is that we just do these kinds of little substitutions all the time, especially when I'm graphing, that it's a lot faster to do this synthetic substitution. And it's interesting because I know first hour when we were trying this on our own today, so I had my students like actually try direct substitution, and it does equal 23. If you go through it, will work out, it will equal 23, and that's what we found. But we also found that at a table of 4 students, one person got it wrong, and a couple of the other students did it multiple times just to make sure they were right. So our accuracy is much better with that synthetic substitution. And I know it's new, I know it's something different, but we're going to practice it and we will get really fast at it this year. So for example 4, I want to go through and I want to graph. And so I'm putting all of my knowledge together now from the entire section. So I'm going to make a table of values to graph. And I know that good values to use for x are, you kind of want to be around 0. You want some negative, you want some positive. So kind of good basic values to use are -2, -1, 0, 1, 2. So we're going to use those for our x. This is a positive 1 in the front, right? There's nothing there, so it's positive, and it's x cubed. So I would expect a cubic graph to go something like this when it's positive and cubed. So that's kind of the picture of what I'm looking. So what I'm doing is I'm plugging in x values, I'm getting out y values, and then I'm going to play connect the dots and connect the points. So when I go ahead and start out and I substitute -2 into this function, I'm going to use synthetic. So my coefficients are 1, -3, 1, 1. So let's go through and do this. And I would recommend pausing the video and maybe trying a few of these values yourself and then kind of running through mine and checking. So when my x is -2, my y is -21. Remember, it's that number at the end. That's what equals. This is my x right here. This is my y right here. And this is like an ordered pair, my input and my output. Then I'm going to plug in -1. And I'll run through that one again. Next value in my table. 0, I don't really need to do any work for, because if I make my 0x cubed minus 3 times 0 squared plus 0, all of those are going to cancel out and just be zeros. And then I have that 1 at the end. And then I want to try 1. I wish I could write a little bit smaller, but it's pretty hard to do on this computer. And I get a 0, 2, all right, and then I'm going to go ahead and graph what I have. So -2 is -21. I'm not really going to graph that one. -1 is -4. 0 is 1. 1, 0 to -1. So right now I have this. The problem is that is not really the graph shape I'm looking for. I really need for this graph to come back up. So I need to do a couple more points until I get this to cross that x-axis again. So we'll try 3. Oh, there we go, something positive. So when x is 3, my y is 4. And so when I graph that last point, 1, 2, 3, 4, my graph is coming back up. And when you connect them, you just want to try and make a curve. So we're not doing this. This is bad. Don't do that. We are trying to make those smooth curves. So you can kind of see how it's all coming together, right? We're looking at graphing, we're looking at understanding these functions, and so we're kind of using all of this information now. Behavior of graphs, what they look like depending on their degree, what the ends are doing, and then also this ability to quickly substitute to work out those values for the table. So I'm going to use the same beginning values on the next one. And I want to, again, think about fourth degree and negative. So that's going to be one that's going down on both ends, possibly like an M. And then I want to just go ahead and plug in my values. And it looks like my graph goes fourth power, third power squared. There's no x term. There's no linear term, but then there's a constant next to the 0 power term where I've got a 6. So I need to have a 0x in here. Got to have that placeholder. So -1, 4, -1, 0, 6. So I'm going to go ahead and do my synthetic really fast. In class, we actually ran out of time and did not do this. We were just running out of time. -46, that's not a very good graphable thing. Let's try the next one. And I get a 0. All right. And then the next one is when I plug in a 0. So same thing again, when I put zeros in for all those x's, I'm left with that constant term that's a 6. So now I'm going to plug in a 1. And then we'll do one more value after this and we'll kind of graph and see where we're at. So we're really after that kind of behavior that we know the graph is supposed to have. So we're graphing, but we're kind of thinking while we're doing it, making sure we understand what's going on. So I have 8, and then let's try 2, and then we'll check our graph. And I know that you're not as fast as I am yet, but you will be. All right, I'm going to go ahead and graph and see what I have. So obviously -246 I can't graph. It's going to be something way down here. And then -1 is at 0. 0 is at 6. 3, 6. 1 is at 8. 2 is at 18. I'm just going to randomly make points up here. I don't have, it's just going up right now. And so I kind of need some more stuff. I know the graph's supposed to come back down. So let's try 3. Hopefully we'll get lucky. There's always that moment of panic, like how many more points am I going to have to do? So let's try 3. But unfortunately, like with everything else, all this synthetic stuff takes a lot of time. 24, so it's just going up further. All right, and I don't have a very pretty smooth curve. Let's try 4. All right, hopefully this will be it. -10, there we go. So 3 was 24, and then 4 is -10. So finally my graph is coming back down. So we'll just make it go like that. There we go. So it's doing some kind of weird, like, kind of like that is what the curve I end up with there, which looks great. So I hope this helps clarify anything you weren't sure about. If you have questions, please ask them in class. So basically, we are looking beyond quadratics. We're going to be solving equations, graphing equations, working with equations that have degree bigger than 2 now. So we want to get comfortable just kind of predicting what they look like and just doing some basic graphing today.